Okay, let's get back to this. I'm going to do 2 examples today. Once I finish, I'm going to go over this kind of general explanation, review a little bit of what we talked about yesterday, and then we'll see where we're at. Hopefully free you to work on some stuff. So, projectiles. By way of review, a projectile is any object traveling through the air where gravity is the only force acting on it. If an object is thrown sideways and an identical object is dropped, they don't actually have to be identical, if you recall. This is not necessary. Based on what I tried to prove to you several days ago, the identicalness is not required, but it's convenient for convincing you if they do happen to be identical. The 2 books I dropped yesterday, for example, if one is thrown sideways and the other one is just dropped at the same time, they do hit the ground at the same time. If they don't, if that doesn't happen or if not, there is some error present in the apparatus, whatever the apparatus is. If the person is the apparatus, or, I mean, the error in the Mythbusters video that I showed you yesterday was within, what was it, 39 point something milliseconds, which is actually faster than, it's a shorter amount of time than a human can comprehend. Your brain is just not able to, so like the error there is just so small. It should happen this way. Because, and that reason is, it was explained in that video and we talked about it again, gravity acts the same on both of those objects when gravity is the only thing acting, regardless of the horizontal velocity. So we started this procedure. We're having 2 objects. I'm going to drop this one with an initial VI of 0. The acceleration is due to gravity because presumably this is on the Earth. We don't know what the final velocity is. We don't know what time this is going to take. And there is some displacement d. This object is experiencing the same displacement d, but this one's getting punted to the right. Horizontally. It's supposed to be a horizontal arrow. It looks kind of askew. And as the bell was going yesterday, I was finishing this thought. Because this is true, a horizontally launched object and a vertically dropped object from the same height will hit the ground at the same time. Because that's true, what that means is that horizontal and vertical portions of this problem are independent of each other. It means they don't interact with each other. And because of this, what we can do is we can actually split the problem into the x, or horizontal, and the y, the vertical. And each portion of the problem is going to get handled independently. There is one concept that links these 2 sides, and that is this. Because they hit at the same time, what that means is the time the object travels sideways is going to be equal to the time it takes the object to drop. This is the concept that links these 2 sides. So we've spent some time, and I saw in your guys' quizzes that I glanced at while I was ordering them that we're getting better at recording the information that we know about a particular problem. For a task like this now, we're going to have to start splitting them up. So let's do all of this. What do we know about anything? Velocity initial, acceleration, displacements, final velocities, for either of these 2 columns. Times are equal, so that's great. We don't know what the time is. We do know that they're equal. We saw that yesterday. The time to drop is going to be the same as the time to fly sideways. So for this singular object, as it moves to the right and drops, what's true. I'm going to put a little subscript x here on all of these, and a little subscript y here on all of these. What can you tell me about anything? Or should I ask some leading questions? Let's focus on the vertical, because that's the same thing we've got over here. This vertical and the vertical portion of this problem are going to be similar. Do we have an initial velocity for this guy in the up-down direction? No. So VIY here, just like VI for the dropping problem, the vertical drop has a 0 initial velocity. Is this object accelerating vertically? Yeah, because gravity's acting on it. And so the acceleration vertically is going to be negative 9.8 meters per second squared. What does the displacement have to be for this object vertically? Based on what I've drawn. You always look like you know and just don't want to say anything. Except I specified. As much as I've drawn, I labeled this vertical displacement, you know what, and maybe let's make this even clearer. That ball is going to drop how far? Based on what I've labeled there. Sorry? No, I have not drawn a platform. I was drawing that these two objects are level. We called this one D. This one has a vertical displacement of D, whatever that value is. This one's also going to have that same vertical displacement. We know what it is. It's whatever this distance is. Whatever we set it to be, thus it shall be. So we have no initial velocity. We've got a vertical acceleration. We've got a vertical displacement. We don't know what this is, but we could calculate it. So this column here, the vertical portion of this object, looks an awful lot like all the information we have for this object that's just getting dropped. Well, maybe I'll label this even clearer. This guy's being dropped. This guy's getting kicked sideways. So let's look at the x portion for this. This guy's also moving sideways. Let's give it some initial velocity VI. I don't know what it is. So if I kick this thing to the right, or throw it to the right, or whatever is being done to project this thing to the right, that initial velocity in the x direction is this value right here, VI. If gravity is the only force acting on this object, is there any acceleration left or right after it's already moving? No, there isn't. There is no acceleration in the x direction. We have no idea how far this thing is going to fly. We'll leave it blank for the time being. What do we know about the final velocity in the horizontal direction for this object? If it's not accelerating, what should this value be? No. If it's not accelerating, it can't change. If this is 0, this has to be the same as this. Here it is. Is that what you're about to say? They have to be the same, yeah. Because there's no acceleration, your final V is going to be the same as whatever it was initially in this horizontal plane. And because there's no acceleration, we actually have a formula to find how far this thing moves in the x direction. Because there's no acceleration, dx is just going to equal Vx times t, whatever this t value is. Maybe it would help if we actually did a couple of these problems. Flip the page. A big, open, blank canvas. Let's do a couple problems, shall we? Okay. So, do two. So I'm going to split the page up in half. And we're going to do two problems. First one. Here we go. Draw it out. We've got an awful lot like Hangman. Oh, Diego, you can say, no, who's kicking soccer balls? Here it is, kicking soccer balls? No. Who said that kicking a soccer ball particularly well was you? Syra. Okay, so Syra is up here with a soccer ball. She is going to punt the soccer ball. How fast do you think you can kick that soccer ball, Syra? If it's impressive, how fast are we talking here? Pick a number. 20? It's actually convenient because, believe it or not, that's the example I'm going off of. 20 meters per second. Here we go. So Syra is able to kick a ball at 20 meters per second, which is in fact very impressive. And she's kicking it straight to the right off of, I don't know, she's on the roof of the school. You know what? Simran's hanging out over here. And the question we're going to try and figure out is, based on the fact that Syra can kick a ball at 20 meters per second, what we want to figure out is, where does Simran stand to catch the ball? That's what we're going to try and figure out. So as soon as Syra punts this ball, it's going to start moving sideways. And as soon as it starts doing that, it's also going to start doing what? It's going to start to fall down. So this ball is going to follow a path that looks something like this. And for those of you who are currently in pre-calculus of Math 10, this shape is something that you're going to be annoyingly familiar with over the next week or so. This trajectory is parabolic. This is a parabola. But because it's a parabola, that means it's awesome because we have an equation that governs the shapes of these things. So when you've got a problem like this, we need to start breaking it up. This is a two-dimensional problem, and I've tried to convince you over the last class and a bit that the vertical portion of the problem and the horizontal portion of the problem are independent of each other. They both exist, they're both happening at the same time, but they're independent of each other. So what we're going to do is we're going to split this thing up, and all of the information into x and y portions of the problem. Now, because we're working in two dimensions, we have two decisions to make here. We need to decide what directions we want to call positive. There are four of them, left, down, up, and right. What directions do you want to call positive? Up and right, okay. Let's label that. If up is positive and right is positive, that's going to dictate the positives and negatives on our values that are going to go into this chart. So what do we know? Well, first of all, we know that the velocity in the x direction It's going to remain constant because nothing is accelerating it in that left-right plane. The ball does not have wings, and we're ignoring air resistance. Because assuming it's not windy, there's not going to be a lot of it. If there is wind, that's a different story. Nope, because it's really hard. Because air resistance depends on the shapes of objects. It also depends on how fast the objects are going. Like, it doesn't scale nicely. The math required is beyond us. You. Math required is beyond you guys. I've seen it once. It's awful. Vx. What is the velocity in the x direction? It's labeled. It's what Cyrus said she could kick the ball at. The velocity in the x direction is 20 meters per second. And the velocity initially in the y is, she's punting this thing flat. So to start, does it have any vertical velocity? No. VIY is equal to 0. It's not accelerating in the x direction because the problem starts after the ball has left Cyrus' foot. But vertically, we have an acceleration. Assuming that, Cyrus on the earth kicking this ball, the acceleration vertically is going to be what? Say it. Negative is going to be really important there because, Lena, you declared up to be positive, so this has to be negative. 9.8 meters per second squared. Now we need to know how tall the building is. Ballpark this, shall we? Let's call it 40 meters. That's probably a little high. No, that's not 40 meters. That might be 40 meters. Let's call it 40 meters. That's probably a little high. But for the sake of the problem, let's use that value. So then, what is the displacement in the y direction? Remember, displacement is the change in the position from the beginning to the end of the problem. It's not going to be 40. It's almost going to be 40 meters. Lena said that up was positive and the ball is moving which way? The ball is ending below where it started. Lena said up was positive, so this has to be negative 40 meters. Or you're going to run into the problem that Lena ran into on your quiz yesterday when she was trying to take square roots of negative numbers, and that's why. So this is all we've got. We've got a VIY equals 0. We've got an acceleration in the y direction. We've got a displacement in the y direction. We have a velocity in the x direction. There's no acceleration. What we want to find is a horizontal displacement. We don't know how this thing is going to move left and right. That's what we're trying to find out because we want to know where Simran has to stand away from the building to catch the ball that's being punted by Syra from the roof. So this is what we're trying to find. Conveniently, the only thing that connects these two problems are the times. These two times are always going to be equal because the ball starts falling and moving to the right at the same time. So, bless you, given the information that we have, we need to find this time somehow so that we can then find this. Given the information available to us, we have to use this side of the problem to find time. So, what kinematic equation are we going to use given this information? We've got a VI, an A, and a D, and we want to find T. I've got one of these over here somewhere. Which one are we going to use? Cyrus pointing. Which one you point at, Sarah? That guy? You bet. So D equals VIT plus 1/2 AT squared, and this is what we need to use to solve for time. So our displacement is -40. VI is 0, which is awesome. The acceleration needs to go in as -9.8. If you look at what we've got here, the displacement and the acceleration both need to be negative. Otherwise, when we're going to find time here, we're going to square root something negative, and that's going to be a problem. So we're going to have -40 equals -4.9 t squared. I'm going to divide by -4.9. And so we're going to get t is equal to the square root of, well, it's going to be basically 8. 40 divided by 4.9, 8.16. I want to square root that. 2.86. So what this says is an object thrown sideways, and it doesn't actually matter how fast it's thrown sideways, because that doesn't show up here at all. Whether it's dropped or kicked sideways, it doesn't matter. It's going to take 2.8 seconds to hit the ground. Now, Sarah has punted this thing sideways, so the only difference is instead of landing right beside the building, it's going to land out here somewhere. And now, because we know how long it's going to take to hit the ground, we can figure out how far horizontally it's going to travel in that time. So then this value for the time is going to become that value for the time. Because it's not accelerating horizontally, the distance in the x direction, which we also call the range, how far is this thing going to fly, is going to equal v times t. Well, we know the velocity in the x direction is 20. We know it's going to travel for 2.86 seconds. So Cimarron is going to have to stand how far away? $57.2 meters on a windless day. In order to catch that soccer ball. Questions, comments, concerns? Follow everything I did? You think you could replicate it yourself? Okay, let's do one more. I'll do one more example for you guys, and then I will free you to play with this stuff. There's only so many things here that we can change. So we used this example to calculate how far horizontally the ball flew. The only other things that we can start tweaking are how high the thing is punted from and how quickly the thing is being punted. So, I mean, I could do 3 examples, but for the sake of this, it's going to get a little bit repetitive. We'll just do 2. So let's say, I don't know, let's pick on someone else. Let's go with Bobby. Bobby, do you know how hard you can kick a ball, Bobby? Let's find out, shall we? So Bobby's up on top of a roof. A really easy thing to measure is how high that roof is. You just need a long enough tape measure. Or my daughter watches a lot of Curious George. He uses a strand of spaghetti to measure the height of a building. let's say that, Bobby, you are able to find an open roof of a building. I don't know, let's say you're 10 meters up. Nice, easy 10 meters. And you kick the ball. You manage to kick the ball perfectly flat. And you have a friend over here, let's say Akash is hanging out over here. And Akash has a tape measure attached to the bottom of the building, and he runs to where the ball impacts the ground. And he is able to measure that you are able to kick the ball such that it lands, I don't know, let's pick something particularly impressive. You're kicking it flat from a 10-meter building. I don't know, let's go 40 meters this way. Now, based on this information, we can actually work our way backwards to figure out how quick the ball had to have left Bobby's foot for this to be true. This is easy to measure. This is easy to measure. Let's try it. I've got X and I've got Y. Let's write down what we know. We know a few things. We know in the Y direction, the initial velocity is 0. In the X direction, this is what we're looking for. We know that in the Y direction, this thing's accelerating. Now we need to call things positive or negative. For the sake of this particular example, I'm going to flip things. I'm going to call down and right positive, just to show you how it changes if you do that instead. If we call down positive, now your acceleration is also positive. So we're going to call A positive 9.8. It's AY. Meters per second squared. We know dy. Now, because down is positive, even though the ball is falling down, this is going to be positive too. We're going to call that 10. We don't know how long that takes. We don't know VI. In fact, that's what we want to find. How fast is the ball going to leave Bobby's foot? We know it's not accelerating in the X direction. Once it's left his foot, it's going to maintain that speed until it hits the grass. We know dx because Akash is going to measure it. The ball is going to impact somewhere. We measured it to be 40 meters. To find VI in the X direction, all we need is the time. We know how far the thing moves sideways. We know it's not accelerating. We need to find the time. And we've got enough information over here to find it in the Y column. And these two, again, have to be equal. So it's going to be the same equation. D equals VIT plus 1/2 AT squared, and we're going to use all of the Y information to find the time. So this is being displaced vertically 10 meters. It has no initial Y velocity. So it's going to be 1/2 9.8 T squared. So this is going to be 10 equals 1/2 times 9.8 is 4.9 T squared. So T is going to equal the square root of 10 over 4.9. That value, for the sake of time, is 1.43 seconds. This time is going to be the same. vertically as it is left and right. It wouldn't make sense for these portions of the problem to start at different times, so they have to be equal. And now we can figure out how fast this thing was moving. We know that d equals v times t, so v is going to have to equal d over t. The distance traveled horizontally, Akash measured to be 40 meters. The time we just calculated to be 1.43 seconds. (40 divided by 1.43). The ball had to have been moving at 27, actually 28, rounding this to one decimal place, 28.0 meters per second. So using this setup, assuming you can measure the height that you're throwing the thing from and the distance it covers until it hits the ground, you can calculate how fast that thing has to have left you for that to be true. Cool. Questions, comments, concerns? Now okay, if there are no questions, Akash, you following what's going on over here? Because you can spend most of that class playing your game. Okay. I'm going to give you guys a choice where you move from here. We've got some time. These two problems are what we're going to tackle next. I have time to do it now and space to do it. Or I can let you practice these 6 questions over the next 40 minutes, do a lab tomorrow, and then come back to these 2 nasty problems on Thursday. What would you prefer? Should I just give all of it now, or do you want some time to play with this? Do you want the time to play? Okay, cool. I'm fine with that. So leave this page empty. I'm going to use it for those last 2 nasty questions. And I want you guys to take a look at these 6. I want you to do all of them. The setup is the same. Draw a picture, separate them out into their horizontal and vertical components. And you're calculating a bunch of stuff. Sorry? Oh, the back page? Yeah, sure, of course.